start our let's start our work today, and we begin a new spring semester of our seminar. It was uh, it was since 30 years when we begin this seminar at our Department of Random Processes. And now we have a talk of Souheyl Jendoubi from Tunisia, from Laboratory of Stochastic Analysis and Applications, University of Tunis El Manar. The title of the talk is Ornstein and Uhlenbeck operators induced by the Berezin Weyl Segal Bargmann Fock models. Please, Souheyl.
Thank you very much. Thank you very much for this opportunity to give a talk in the Malliavin calculus seminar and its application. So my talk is about Ornstein-Uhlenbeck operator and especially how these operator are induced from some algebraico-geometric model. So this work is a joint work with Hélène Héroux from the University of Picardie-Gilles and Habib Warden, the ex-head of our laboratory. So, the planning of my talk is the following. First, I will recall some property of the real Euclidean Ornstein-Uhlenbeck operator and process. Then I explain the method proposed by Héroux and Warden to construct the Ornstein-Uhlenbeck operator in some geometric model using Lie theory representation and their infinitesimal representation of their associated Lie algebra. And we give here some expansion of the Ornstein-Uhlenbeck operator in terms of generator of the infinitesimal representation. Especially here, we shall consider some nilpotent Lie group which are representable on Fock space. Here's a photo of Hélène Héroux and Habib. So the classical heat semigroup is a Markovian semigroup defined by the expectation of Fx plus Bt, where Bt is a one or d-dimensional Brown motion. This semigroup has an infinitesimal generator given by 1/2 of the second derivative here in one dimension or 1/2 of the Laplacian. So some perturbation of this semigroup is related to the classical Ornstein-Uhlenbeck operator and process defined on R or Rd. And the process satisfies this stochastic differential equation, dxt minus xt dt plus square root of 2 dbt. And by the E2 formula, we get an explicit expression of the process. Furthermore, the generator of the Ornstein-Uhlenbeck semigroup is given by the third property is the limit of 1 over t nt minus f, and it's equal to the Laplacian minus the Euler operator. That is the Ornstein-Uhlenbeck operator or process. We can see it as a perturbation of the Brownian case. So many investigations in physics or in stochastic analysis related to the Ornstein-Uhlenbeck semigroup, which is symmetric, and also its generator. In particular, it is invariant and has the Gaussian measure, the standard Gaussian measure as stationary distribution. That is the integral of LF d gamma dx equal to 0 for all C2 functions which vanish at infinity. So the problem given by Warden and Eru that is, does exist, for example, an analog of such phenomena on complex domain of C or of Cn. So here we shall consider an analog in the complex case, that is in the whole plane C. So the complex, the one-dimensional complex Ornstein-Uhlenbeck process was physically interpreted as the fluctuation of an electric charge in the presence of a constant magnetic field. For example, sorry, here I haven't put the reference, but it's reference the last work of Chang Wang and Liu Yong in 2012, I think. They studied eigenvalue and or eigenfunction related to this complex Ornstein-Uhlenbeck operator, and they cited in their work that this process was firstly investigated by Kolmogorov in his work on perturbation theory.
Souheyl, can I have a question?
Yeah.
So in equation 7, this complex valued Brownian motion is the process which can be interpreted as two-dimensional Brownian motion or not?
Yeah.
Yeah. So it is the same, only we just have imaginary unit. Okay.
Yes.
That's,
Yes. It's BT1 plus I BT2 with two independent Brown motion.
Okay, so this equation 8 is just the form how to express the usual Ornstein-Uhlenbeck operator, which we discussed before, in a complex in terms of complex numbers. Yeah.
Yes. Just I will give the expression of this derivative in complex coordinate. In real coordinate, for example, dz equal to 1/2 dx minus I dy for
I
z.
see, I see. But let me ask you the following.
Yes.
When we discuss such form of presentation of a Stern-Beck operator, maybe we have to discuss the special functions from the domain of definition, because usually when we have a complex derivative, we just think about analytic or holomorphic function. Yeah? Is it right?
Yes, yes. Here, but for example, holomorphic function vanish with if we derive it with respect to z bar. So
Yes, yes, exactly. So it was my question. Yeah, exactly.
yeah,
So how can we interpret this expression? What we have to require from the function from domain of definition in the sense of
yeah.
complex number?
Yes, for example, for the inverse, we can prove that the domain contain C2 function which vanish at when the model of Z go to infinity, or for
So
example,
we just have not pay attention to this analytic property. This d over dz is just linear combination now of partial derivatives. Yeah.
yes, is
Mhm.
1/2 dx minus I, the
I
complex
see. I see.
I dy.
Okay. Okay. So it is now it is just a convenient form of the presentation of the formula. Yeah.
Yes,
Okay. Thank you.
thank you. So the main goal of my talk is to not to express the analytic background around this operator, but I will present some algebraico-geometric structure such that this operator is induced in our strategy of work. So that is, does exist some groups or some Lie algebra such that we can define this operator. So I will consider some locally compact, simply connected Lie group here of the complex linear space, linear group, that is the group of complex matrix that are invertible. I assume that the group act holomorphically on C, that an action is just a map from G times C in C, satisfies some cocycle relation, we shall express it later, and we shall consider, we shall represent our group in terms of linear operator. That is a representation of, we shall take a special representation, that is a composition by the action Kj, that is the action of our group on the plane, and we multiply by a scalar function from G times C on C. That is our operator Tg is labeled by an element J in the group. And this action is holomorphic. That is holomorphic in Z. So this type of representation was investigated by Berezin and
Again, let me ask you, when we say representation, usually we want to have some action of linear operators, yeah?
yes,
In
here
some space. So we consider now the space of function f capital, which is integrable, yeah, or what?
yeah, yes. That is here. I will construct unitary operator from the group. That is, for each j, Tj is a unitary operator acting on some space of holomorphic function.
And
And
unitary
square
with
integrable
respect
also.
to the yes, with respect to the norm of f in L2 norm of f, yeah.
Yes.
With respect to some measure, maybe with respect to Gaussian measure, yeah.
Yes, that is
Okay.
the reference measure or the reference here, which shall represent it on some reproducing kernel Hilbert space. We have the reference is the Fock space. Is the space of holomorphic functions were integrable with respect to the Gaussian measure on C. Yes, our representation here maybe satisfy the condition 1 and 2 if it called, if it satisfies condition 2, it's called a Weyl representation, or sometimes they call it in quantum physics they call it projective representation. That is, the composition is a scalar constant dependent on the group multiplied by Tg1, Tg2, where G1, G2 is the product in the group. And the map C here is in C1, that is in the unit circle of C. So our aim also, we want to here in order to obtain this condition 2, our composition and multiplication factor for the representative operator shall satisfy the two cocycle. That is, this equation in green, this it's come from the definition of the action of the group on the C, and the second one is related to the composition of Tg1, Tg2. So, and the third condition, we want to consider unitary operator, EJ. That is a unitary in sum reproducing kernel Hilbert space of holomorphic function with respect to some probability measure on C. And we assume that we have reproducing kernel Hilbert space, which I'll give in the following some example related to Fock space and some perturbation of the Fock space. And our scalar product is given by the integral of the product F1, F2 bar d mu. And here we have some measure. This measure, we want to take here a special case of representation. That is, since we know that the Uhlenbeck measure here is rotation invariant. So we take kj, the action of z plus a function of g, and the multiplication is exponential lg plus mgz. Here, like a polynomial of degree 1, which depend of the group element, where M is a group homomorphism from G to C plus, and L is just a mapping from G to C. And in order to obtain a Weyl condition, the map here, CG1, CG2, is equal to this quantity exponential LG1 plus LG2 minus LG1, LG2 minus M multiplied by UG1. And it is here in the, for example, if L is also a group homomorphism, we obtain just exponential mg2 ug1. Furthermore, if there exists a positive continuous map, theta, such that we have this equation, here, well, RE means the real part of this complex number. Our representation given, sorry, here, given by equation 12 is a unitary representation into the space of holomorphic function, which is square integrable with respect to the measure with density theta. So the problem is to prove that our measure is invariant for some secondary differential operator, here D in general, but here in our case D equal to C. And this operator shall be called an Ornstein operator type. And here the class of test phi, for example, should be in a suitable class of test function satisfying this relation. Not obligatory, that is holomorphic function, just a test function in the domain of the operator delta. That is, here we shall construct an analog of the Ornstein-Uhlenbeck phenomena. So from this, the previous algebraic setting, how to obtain differential operator. This is the question now. And if we use the so-called infinitesimal representation or derived representation associated to a Lie group representation, here we shall consider the Lie algebra associated to our group. Just here to introduce quickly the Lie algebra, it is the set of all X of all complex matrix, such that exponential Tx belongs to the group J, because here we consider a subgroup of matrix. So, and the Lie algebra is all the set of all x that this is in the group, in our group J. And for each element x in the Lie algebra, we define an operator called the infinitesimal representation that is a map from the Lie algebra J to the endomorphism of a homomorphic function. And it is defined by the derivation with respect to t, tgt, fz. If we consider, we rewrite our representation for any j, and we replace by this j indexed by t is just a curve on the group passing by the identity, we obtain that the infinitesimal representation is the first order differential operator. Just we denote AXZ is the derivation of at zero of the action, and BX is the derivation of the multiplication function HG. Thus, we obtain rho x is written as the first order differential operator, that is we call it holomorphic vector field, plus a scalar function scalar holomorphic function depend on x and on z, multiplied by the identity operator. So from this setting of differential calculus, and using the Cauchy-Riemann notation, that is which express dz and dz bar, we want to define what we want to construct, that is called Ornstein-Uhlenbeck type operator, which is invariant with respect to the unitarizing measure of the representation. So we shall call a second order differential operator is of Ornstein-Uhlenbeck type if it has the form that is a second order with the weight A multiplied by like the classical Laplacian here, because we work on the Euclidean space, and this first order differential operator, where the coefficients are continuous functions depending on z and z bar. Furthermore,
Souheyl, can I ask you that at least from in general case, it is not evident that A and B cannot be zero, yeah? For example, A cannot be zero, that you will get only the first order differential operator, yeah? For example, let your Lie group can be rotation in the plane, yeah?
yeah, here for the derivation.
Mhm.
So here is usually we have with this form what we taken, we have a first order differential operator.
Yes, surely, surely. So the question is, maybe you have to present, or you will present the condition on the Lie group under which we will have the second order term. Yeah.
Yeah, yeah.
Okay.
Yes, so we want to construct a second order differential operator that is invariant with respect to the measure d mu. So if we have a unitary representation here, we shall define a notion which called induction of the operator from the geometric structure. Here we have a quantuple that is represented by the group, and the state space where the group acts, the representation, and the measure, and our infinitesimal representation, which is the first order differential operator, depend on the Lie algebra. And we say that this geometric structure induces an Ornstein type operator if there exists an Ornstein-Uhlenbeck operator that is second order and invariant. Furthermore, if delta, the second order differential operator, has an expansion with respect rho x, and hx is just the first term in the derivation, and or their complex conjugate. So, in the sense that if we have a basis of, because here we work with finite dimensional Lie groups, that is like dimensional of the Lie algebra is equal to the dimension of the manifold, that is a result on geometry in geometry. So if we have on here a basis of the Lie algebra, if there exists some family of constant such that our operator can be expressed by rho v and hv in this sense. So because rho v is just a first order differential operator with respect to dz plus the constant part. So if we take some conjugate here, we have this possibility to obtain the Laplacian. And in the following, we shall give two examples. The first one is the Heisenberg group. The Heisenberg group here is C times R equipped with this law. And in the second coordinate, we have this B1 B plus B2 plus imaginary part of E1 bar E2. And we express this group as we take the group realization. It can be written in this form. So here the model of A plus IB in the second, that is a subgroup of 3 times 3 invertible matrix. A basis of the Lie algebra here is consists of 3 matrix x1, x2, x3 with a Lie bracket equal. Only we have node 0 Lie bracket x1, x2 is 2x3, where the bracket is the product of x1, x2 minus x2, x1. And the other Lie bracket are 0. In fact, here we have some gradiated Lie algebra. It is called of two-step. And our result here of just here, I calculate the curve or the curve passing by the identity related to related to the generator of the Lie algebra, x1, x2, x3. Concerning the representation of the Lie group, the Heisenberg Lie group, so I consider a representation from a monograph of Jacques Farou and Khalifa Harzala in a summer school in Tunis. They used it in some context. So we consider here the group and we represent on the Fock space equipped with the measure here absolute value of sigma over p, where sigma is an arbitrary non-zero real number. So in this result, there is exactly two inequivalent class of holomorphic unitary representation. That is there is no an invertible operator such that S sorry, I will give these two. Okay, here. So in equivalent, that is, there is no operator such that Tj equal to an invertible operator S and J composed with S minus 1. That is equivalence in this sense. And the first one is constructed for sigma positive, that is the action here is just translation by Z and with this multiplication. And we prove it's proven that that's just fact that is unitary into the Fock space with the variance, we say sigma. For sigma negative, we have a representation that is related to first one, but in this way. So we shall denote the infinitesimal representation related to the to sigma positive by sigma plus, and for the negative one, sigma minus. So for the positive value of sigma, we have there's three operators. So the two first one are a first order operator plus a constant term. The third one is related to the center of the Lie algebra. Here just we have a constant multiplied by the identity operator on holomorphic function. So for this operator here, just to obtain this operator, we take holomorphic unitary representation, and when we take the derivation, we lost the measure. That is, this operator act on only on holomorphic space of C. So for the second one, we have also there's the three first order operator. We shall denote by delta gk equal rho xj, where xj is the basis of our Lie algebra. So we take rho xj plus the conjugate composed with the bar of hxk, where hk is a constant multiplied by dz and dependent on the Lie algebra and dependent on the representation of the group. So the first result here is for each sigma and for each representation and geometric structure presented previously, we have such complex operator given by 1/2 of delta 1 plus 1/2 of delta t2, where delta 1 here just rho x1 plus rho x1 bar composed by hx1. The same thing for delta 2. For delta 3 is equal to 0. Just this operator delta 3 because we haven't this derivation hk. And here we have this operator and its conjugate. If we add the conjugate here of equation 34, we obtain 2 the Laplacian minus absolute value of sigma z bar dz bar, and we obtain the well-known Ornstein-Uhlenbeck operator, which is invariant with respect to the Gaussian measure, and this is the induction of the Ornstein-Uhlenbeck operator from the Heisenberg geometric structure. In the following, we ask what happens if we take not an equivalent representation. That is, if we perturbate the representation of the group, what happens on this expansion of the Ornstein-Uhlenbeck operator? So here we shall consider the probability measure that is leaves that's equipped, that is the intersection of holomorphic function with L2 with respect to this measure is a reproducing kernel Hilbert space. This Hilbert space called generalized Fock space or twisted Fock space. It is discovered by Driver and all in their study on some quantum field. Also, it is generalized by Fabeck, Olafsson, and Sengupta for reproducing kernel of holomorphic space on Cn. And here we shall present the dimension 1. Here, that is the measure depends on its analog of the real measure with the matrix covariance, but here that is the plus here is that is leave function as a reproducing kernel Hilbert space. So if we take the absolute value of sigma equal here, just or also I give an example here. Here, if equal sigma 1 plus sigma 2 over 2, we construct a unitary operator from the Fock space to this twisted Fock space, this perturbated Fock space. Here, if sigma 1 equals sigma 2, we obtain the classical one. Moreover, this operator is intertwines the representation Tj to a new representation, holomorphic representation, that is unitary with respect to the measure d mu sigma 1 sigma 2. And this intertwining property is given in the equation 35 in this sense. We construct a new representation, e.g. sigma 1 sigma 2 is m composed with Tj composed with m minus 1. And Ej is called an equivalent representation related to Tj. The same thing we do with Nj for negative value of sigma, we obtain a gamma j. Explicitly here, we obtain the following representation. Sorry. Yes. So here, this perturbation doesn't affect the action, the composition, but the factor here, there is some new term. For example, here we denote by sigma bar is equal to sigma 1 minus sigma 2 over 2, just notation. Sigma here is a real number. Just for the notation here in the coefficient of z in the exponential for the two representation. And this perturbation in the automorphic, in the Weyl factor, what is the multiplication of fz plus a, sorry. So affect, we prove that it's affect, not affect the weight in the Laplacian, but it affects the drift bar. That is the first order differential operator in the Ornstein-Uhlenbeck operator. So with the same machinery of infinitesimal representation for these two, now there's the infinitesimal representation associated to the new holomorphic representation presented. And if we recall this delta gk equal rho x gk plus its conjugate composed with hxk, we obtain the same, we obtain not the same, sorry, not the same operator, but a secondary differential operator, where here we have a presence of, in the first one, sorry, here if we take sigma 1 equals sigma 2, sigma bar equal to 0. That is equation 45 becomes the Laplacian minus the absolute value of sigma z bar dz bar. Here we have the new term sigma bar z. And also it's the conjugate of this secondary differential operator is invariant, and we conclude that there's two perturbated geometric structure induced an Ornstein Uhlenbeck type here that is related to the measure. Here for the new measure, just if we, sorry, I will just speak about this twisted measure. Here, if we use the complex number, we we can write in exponential minus the sum of sigma 1, sigma 2 over 2, zz bar, plus sigma 1 minus sigma 2 over 4, multiplied by z2, z power 2 plus z bar power 2. That is a perturbation term that is what different which make the difference between this measure and the classical Gaussian measure. So another example, sorry, here I will. So another example here, and is to take the so-called angle group is G4 equipped with this multiplication law. So in the three first coordinate in the multiplication is like the Heisenberg group, but in the fourth one there is some function of the coefficient A1, B1, A2, B2, and C2. And this group is identified to a closed subgroup of GL4 by a natural representation here, and we represent this as a matrix Lie group. And its Lie algebra has four generators: x1, x2, x3, and x4, where Ej here is the canonical basis of M4 of R. Shall consider a representation used by Gordina and Haga in the construction of and studied of quantized generator of Levy process on a three-step nilpotent Lie group. So this representation is an L2 representative, that is unitary on L2R du, the classical L2 space. So from this representation, we can construct an holomorphic one. That is by using the Segal-Bargmann transform, which is an operator from L2 to here we denote HL2CD gamma is the Fock space with sigma equal 1, but we can write it with any sigma. And what is important here, that is, this operator is invertible, and its inversion is given by B1 minus 1. This is the result of Bargmann in his study of Bargmann space. So, to obtain Weyl representation here, just we write the intertwining identity Tj is B1W B1 minus 1. And we obtain this holomorphic representation in the Fock space, where our representation here is labeled also by some real number tau. Tau is appear in the factor and also in the composition of the representation, where A, B, C are where G is equal to A, B, C, and D. Then the infinitesimal representation here is given by for operator depend on the basis with for this case rho x cut x4 is equal to 0, and we observe that the second derivation rho x2 and rho x3 depend on this parameter 2. So we prove that if tau is non-zero real number, this p square tau square delta 1 plus delta 2 is equal to also to this Ornstein-Uhlenbeck operator. And this is the induction of the Ornstein-Uhlenbeck operator from this geometric structure. And if tau equal to 0, we have another expansion that is given because if tau equal to 0, just we have here one generator rho x1 in our case, in this case. Just all the other three operator are 0. So with this generator, we construct the Ornstein-Uhlenbeck operator with this form. It's equal for hx1 x1 bar plus rho x1 minus hx1 composed with and its conjugate. And we obtain this Ornstein-Uhlenbeck operator here which is invariant with respect to the measure gamma. And this is the induction phenomena from the geometric structure of Ornstein-Uhlenbeck operator. So my talk is based on this bibliographic work of Eero Warden, here of Eero Bosaja, the construct Ornstein-Uhlenbeck operator on some bounded symmetric space, and the work of Bargmann and Olafsson. Yes. And thank you very much for your attention.
Okay, thank you very much. Maybe somebody have questions or comments, please. If there are no questions, I have some comments and questions. First of all, it was my pleasure to see the talk where Habib Kordian was one of the initiators of these investigations, because I remember Habib from 2011 maybe, and he was a very good mathematician and very kind person. Even with Noafel Souheyl published a paper devoted to him in Stochastic last year. But about the talk, There are a lot of properties. The first question: there are a lot of properties of Ornstein-Uhlenbeck semigroup in Fock space. For example, maybe well known, this is Nelson hypercontractivity estimations. Did you think about the properties of your obtained operators from such point of view? That they can produce some regularization of the functions and so on.
That is, there exists hypercontractivity, yeah?
Yes,
Property
exactly.
study. Actually, I haven't seen this work of Nilsson, yeah.
I think it will be useful. Even I think that initially in Berezin book method of second quantization, you can find something mentioned about Ornstein-Uhlenbeck semigroup and its properties, yeah, in any Fock space. This is the first question. The second one. I think that the book of Kirillov about infinitely dimensional about representation of infinitely dimensional groups can be useful because the idea related to have representation in the space of L2 functions with shift in the space and some multipliers came to Kirillov. So I think it can be a good reference. Also, the half of your talk is devoted to Heisenberg Engel group, and these are partial cases of Carnot groups. By the way, in our audience today we have Alexey Rudenko, who is a good specialist in probability on Carnot groups. And from this point of view, let me ask you the following question. Did you have you think about the same construction on arbitrary Carnot group?
This is a good question, though. I think it is possible. That is the Carnot is yeah, yes, it generalizes this Rn with some law that is polynomial of the element, yeah, and with this,
Exactly. I think that always will work.
yeah, yeah,
And the second question is actually this question is due to Alexey Rudenko constructions because in Carnot group we have Brownian motion, yeah? We have a Brownian motion. And how this Brownian motion is related to your Ornstein-Uhlenbeck process? Can we think in such a way that we just get some representation of the Carnot group, then we get related Lie algebra, get the Brownian motion, and get the finally make the perturbation of Laplacian?
maybe
What
there
do you
is a
think?
link. I don't know. Maybe there is a link. Because here the Orsen is constructed on the state space where the group act, not on the group like geometric
Yes, I
structure.
understand.
Yeah,
But you just reduce it using the representation. You can have some motion on the functions. Yes, in L2 space. In L2 space, yeah, you will have Brownian motion in L2 space, and
yeah,
then maybe it can be lifted to Brownian motion of the space and to Stein and back. Yeah.
yeah.
It can be interesting to have the link. Uh, okay, thank you very much.
Thank
Thank
you.
you very much for your talk. And before we will end our seminar, since it is the first in the spring semester, let me invite all speakers and participants of our seminars to prepare papers related to their talks and submit it to our journal Theory of Stochastic Processes. And recall that recording of all talks will be available at our YouTube channel. Then for today's, that's all. And maybe, Katerina, do you know who will be next speaker?
The next speaker will be Alexander Kukush.
Okay, very good. By the way, let me represent to our audience the new member of our department, Professor Alexander Kukush, who will have a talk about some problems from statistics next time. For today, that's all. Thanks everybody for participation and see you next week. Bye.
Thank you. Bye.
Bye.